All right, so here's the Leetcode problem 480 sliding window median. To be honest, if you get this problem, you've probably already lost the interview, but you can maybe hope to God that perhaps if you remember the general concept behind the problem and they're not making you run tests like you're just coding on a text editor for the interviewer, maybe you can pull one over on them. But yeah, coming up with a solution for this is extremely hard, even if you know the base concept of the problem. It's so hard that NeetCode himself put it in his course on using the two heaps approach, but he didn't actually implement the solution for this problem. So I don't know. I think he's just too much of a coward to do it. Obviously, he's doing all these other random problems, but he doesn't do his own problem that he recommends doing in his course. I've gone on for enough here. Let's just go ahead and get started. There is a concept here that I've briefly touched on, and that is the two heaps approach. And we know we are going to use this because we are dealing with a medium problem. So when we use a medium, I'm going to go over this lightly. You should actually take a look at the find a median from a data stream question first before you even do this problem. You should solve that problem first, and that will really familiarize you with the two heaps approach. But I'll summarize it in general. You're going to have two heaps. One is going to be on the left and one is going to be on the right. The one on the left is going to be a max heap, and the one on the right is going to be a min heap. And the idea is we're trying to find the median of some set of values that we don't have ahead of time, which is why we're using the heaps, why we can't just go in an array and find the middle of the index. No, we have some dynamic structure of data and we're trying to find the median of those values. And the way we do this is we maintain two heaps. Their size has to be roughly equal, and we'll go more into detail on that later. But for the normal implementation of the two heaps, their size will only be different by one, and that's the case if there are an odd number of elements. For example, let's say there are 3 elements in our max heap on the left. We will have maybe 2 on the left and then 1 on the right. Or another valid, for example, if we had 1, 2, 3, we know here, like trivially, the median is 2, right? But another way to keep track of this would be to have the heap set up like this. So 1 is on the left and 2 and 3 are on the right. It doesn't matter. Basically, we have to look at the heap with more values. So in this case, it'd be the right heap. In the previous case, it'd be the left heap, right? Because the left heap has more values than the right heap, so it'd be 2. And in this case, since the right heap has more values than the left heap, it would be 2, right? So you can see for the same set of values, it doesn't matter what heap has more elements than the other. It just matters that we find the heap that has more elements and we take its top, or we pop off the top, and that is the answer to our question. If there are an odd number of elements, if they're an even number, for example, let's go with the example 1, 2, 3, and 4, then our answer is going to be even easier. We just take the average of the top of both heaps, right? So we can pop off from the left heap or the max heap, pop up from the min heap or the right heap, and now we have the median. We actually don't need to pop them off. We can just look at them. So that's the concept of two heaps. Very simple summary. So how do we apply two heaps approach to our problem? Well, let's read the problem. Our problem is the sliding window median. So it explains to us what a median is, and it tells us we're given an integer array nums and an integer k. There's a sliding window of size k, which is moving from the very left of the array to the very right. You can only see the k numbers in the window each time the sliding window moves right by 1 position. Return the median array for each window in the original array. So this is probably the hardest part to understand, but once we look at the example, it is pretty clear. So we have our array nums. We have our k, which is 3. And now we have this output. How do we get this output? Well, if we look at the explanation, we have this window size 3 for every possible position it can be in the array. And you can see it looks like this here. We've got the first 3, then it moves by 1, and then we have these 3, and then moves by 1, and then we get the next 3, and so on and so forth. Right? For each window, we have to get its median, and then we just append it to some results, and you can see 1, -1, -1, 3, 5, 6 is the output. So that's what we're going for, and that's the concept behind this problem. Basically, we're going to need to modify our original median finder to heaps object or solution, whatever you want to think of it. We have to change it in a way so that we can adapt it to this problem, because our window is constantly changing. The idea is that, in fact, we're going to have to remove values from our heaps, and removing a value from a heap is not simple. It's going to take a lot of time. The whole point we're using heaps, just popping the top of them or looking at the top of them, is constant time. So inserting is log n time, but removing is something else entirely. Removing may take an extremely long amount of time. Yeah, to find the element and then to remove it. So that's the hard part of this problem, is how do we remove from our heaps without screwing everything up. So now that we know that, let's get to the solution. And the idea is that we're going to break this invariant. We're going to break it, but we're not going to break it by removing every time we need to remove. We're going to do something called lazy deleting. And the idea behind lazy deleting is that we're only going to delete these values when they come up to the top of the heap. So that way it's constant time to get rid of the value that we don't want anymore, right? Because let's say we're moving through this array, we are going to get rid of this element, for example, here, right? Like 1, we're going to get rid of it. And then for the next step, we need to get rid of 3, right? But we don't want to do that every time because it's going to take too much time to remove that element. We only want to do it when it's at the top, because when it's at the top, it only takes constant time to remove that element. And this way, this is the way we're going to maintain a decent runtime. We're going to delete lazily. But if we delete lazily, we're going to have situations. Let's look at our example here. So we have k equals 4 for the array nums of 4, 3, 2, 1, 0. And let's just say our max array has 1 and 2, and our min array has 3 and 4. In this case, we take the average of these two values, and the median is going to be 2.5. And that's all fine, but what happens when we need to move this window to the right? Okay, so now our window is 3210. That means we need to get rid of 4 and add 0. These are the two things that we need to do. How do we do that? Well, what we can do is we can see if 4 is at the top. It's not at the top. So if we want to delete 4, it's going to be a expensive operation to do so, right? What's one other way we can keep 4 in our heaps while effectively acting like it's been deleted? Well, the idea here is we know, let's just find what the actual median of this array is. So 0, 1, 2, and 3. It would be 1.5, right? So we know our median is 1.5. So what answer would give us 1.5? Well, let's say we were to move this 2 to the other side, right? We were to move our 2 from our left heap to our right heap, from our max heap to our min heap. So in that case, we would have 1, 2, 3, and 4. Our median is now 1.5, but there is something that we need to take into account. Let's say that this element was not 0. Let's say that it was something like -1, right? So we need to add -1 as an element to our heaps. Where would that go? Well, since -1 is less than everything else, right? Is less than the median, that means we need to put it in the max array, right? Because that's the best way for things to be balanced. So we go ahead and do that. If we take the average of our top of our max heap and the top of our min heap, we do have the answer being 1.5. And how was this maintained? How do we know this? Well, basically, by moving 2 to the other side, we were able to maintain the balance of the heaps, right? Let's say we didn't move 2 to the other side. We would have -1, 1, 2, and then 3 and 4. Then the median would be wrong, right? But we have to move 2 to the other side essentially to force this 4 out of the picture. When we get rid of an element, we have to add an element to compensate for that, right? And that's why we're moving to the other side. Now, there's also a situation where we might not have to do this, and that's if our last element was something like 6, where it's above the current median, where it's above the median 2.5. So let's say it was 6. Now, what is the median of this array? 1, 2, 3, 6. It would be 2.5. It would be 2 and 3, right? So now the median we're looking for, the answer, right, to the problem would be 2.5. So how would we do this, right? We still have to delete 4, right? We still have to delete 4. So that makes sense. But the thing is, 6 is now going to go into the min heap. It's going to go on the right side. So if we were to draw it out, if we were to draw this out, we have an array with 1, 2, 3, 4, and 6. Since now the balance has been maintained, we don't need to compensate for the fact that we got 4. We can just add 6 to the right side. And because of that, because we didn't change anything, now the 2 and 3 being the elements that we need to find the median, that still maintains, right? The problem was before, when our element that we were supposed to add is less than the previous median, that causes a need for us to move one of the elements from the max heap to the min heap. But if there is no need to do that, if we are adding an element to the min heap ourselves, then we don't need to pull from the max heap to move to the min heap. So essentially, what we can do is keep track of a variable, and we're going to start it at 0. If we delete something on the right side, we're going to add 1. But if we're going to add a new element on the right side, then we're going to subtract 1. Then it's going to be 0, because basically we have balanced our heaps. When we delete something on the right, we need something on the right. If we're adding something on the left, that means we're going to have to move something to the right. Does that make sense? If it's the exact opposite. If, let's say, we were to delete on the left, then we would subtract by 1. But if we were to add something on the right, on the left, then we would add 1 to this need variable. So you can see that if we delete on the right and we add on the right, it cancels out and our need is 0. But if we delete on the right and we add on the left, now we have 2. What does that mean? What does that mean? Well, it's like our previous example. That means we have to move from the left to the right. If we have a positive need, let's say need is greater than 0, that means that we have to move from the left to the right. If it's less than 0, that means we have to move from the right to the left, or move from the min to the max. So I hope that makes sense. It'll make some more sense maybe when we code it up. But the idea is that our arrays are no longer going to be balanced. They're going to be unbalanced. And there is one more thing that I need to change here. So for our code, we're no longer going to have the same invariant. We're no longer going to have the invariant where len of min could also possibly be equal to len of max plus 1. Essentially, the right heap before, in a normal 2-heap solution, the right heap could also have 1 more than the left. In our new array system, since if that were the case, we would no longer know which heap had the median, because the sizes of the heaps are no longer going to keep to this invariant where they're only going to be within one of each other. Like min could have like 5 elements and max could have 1. Because of that, we need to make sure that we know which side the median is on. And for our cases, we're just going to make sure it's on the left. So in the case of odd elements, our median is going to be on the left. And also, we know that we are always going to put elements into our left first and only move them to the right if we have to. And I didn't really talk about deleting elements. What we're going to do is keep our deleted elements in like some sort of hash map or a dictionary in Python, right? Just a set. We need to keep track of what elements we need to delete. And when it comes time to delete them, we're going to pop them off the top of a heap. So if in any of the tops of our heaps we see a element that has been deleted, that has moved outside the window, we can go ahead and get rid of it. We can pop it from our heap. So that's how we're going to do this lazy deletion. This way our heaps don't get too large or unbalanced. And that's the idea behind the deletion. And it's important to make sure that when we're adding stuff, we prefer the left. We don't know that anymore since our heaps are no longer the normal 2 heaps. They're not necessarily very well balanced. Okay, so we're going to code this solution up. Well, we need to return a result which has all the medians inside of it. So let's make an array for that. Let's make an array for the left and the right heaps. So the left heap will be max and right heap is min. Okay, what else do we need? Well, first we just need to put all our elements in these heaps, right? So if you kind of understand how a heap is, remember that we have the invariant that left, the lane of left is greater than lane of right. Okay, so because of that, let's do it this way. What we're going to do is for I in range k, I'm going to heap q dot heap push into the left array, and I'm going to push I. And you can see what we're doing is just this first part here where we put the first k elements into our 2 heaps. So first, we're always going to push into the left. Okay, if left and right. So if they have elements and left, we're peeking right over the top. If left of 0 is greater than right of 0, that means when we're peeking at the top of the left heap, the top of the max heap, and it's got an element that's greater than something in the right heap, then we need to move it, right? So this is something you're going to see a lot, is I'm going to push into the right, and I'm going to need to... One thing that's also important is whenever we're pushing into the left or doing anything between the left and the right, we have to make it negative because there are no max heaps in Python, okay? They're all min heaps. So to make a max heap or to make a min heap into a max heap, you have to make all its elements negative for it to work, right? That makes sense. So whenever we're going to have to do a lot of switching between negatives here, which we're going to do by popping from left, okay? And this is going to be a common pattern when we move elements between heaps, okay? So if we also want it to be somewhat balanced, at least to start, right? One way we can do that is if the lane of left is greater than lane of right plus 1, I'm going to move to the right, okay? Conversely, we want to make sure that if lane of right is greater than lane of left, we push from the left, we push into the left from the right, okay? So this will make sure these 3 if statements are going to construct our 2 heaps for us, okay? And yeah, let's say we had 1, 3, 1. Okay, our heaps would look like this. And this is a max heap, so it would actually be like 3, 1. It actually be -3, -1, but just for the sake of principle, it would be, sorry, it'd actually be 1, -1, and then right would be 3. Okay, so that's what we expect when we're in this position in example 1 on the left. Okay, so now we need to find the median. And the median, well, remember when we have even elements in a heap, so if k, the size of a heap is always going to be k, right? So if k, the remainder is 0, or basically we're checking if it's even, right? So if there's an even number of elements, then what we do is we are going to set our median. So let's just initialize our median here. If the amount of elements is even, then we set our median to equal to left 0. And this is negative. Remember, it's got to be really careful about when we're using the left heap, right? Because the left heap is a max heap, so we got to negative it at all times. And that's our median, right? Now we can go ahead and append our median. What if there's odd? What if there's odd number of elements though? What do we do? Well, remember, since our invariant is that our left heap is always going to have more than our right heap, we're going to set the median to left 0. And not just left 0, we're going to set to negative left 0. Okay, so now we've finished with this part where we initialize the heap. Now we have to do something a little bit more complicated, right? So for j in range k to length of nums, okay? So what j is going to represent here is this element, okay? So the element that we're adding. So j is the index of the element we're adding at each part of the array. Does that make sense? So when j is 3, right, 0, 1, 2, 3, we're talking about negative 3s here, okay? So what is the element that we need to remove? Well, first let's keep track of maybe a dictionary of elements we need to remove, okay? So remove dict, and I'm going to make it a dictionary by using the collections library. I'm going to call default dict int. So we have a dictionary where the default value is 0. This is kind of useful for us, so we don't always have to check things. So we have a dictionary to keep track of the elements we need to lazy delete later. And the element that we need to delete later is nums k minus, it's nums j minus k, right? Let's say we're at element 3 here. The element we're going to need to remove is 1, right? So this is the element we need to remove. And we can go ahead and set our dictionary so we can keep track. Okay, that's the element we need to remove, okay? Now what's next? Well, we need to figure out that need variable we were talking about earlier to balance the heaps, right? So need is equal to 0. Okay, so let's say we had the example of an array nums with 1, 2, 3, and 4, and k equals to 3, okay? So obviously when the window is like this, okay, we have our left being like 1, 2, this is our left heap, and then our right heap is just a 3, okay? But when we move this window, so what happens when we move this window to 2, 3, 4? Okay, obviously you can see here that the median that we want, so the median it was before when it was 1, 2, 3 is 2, right? The median that we want now is 3. So how do we get that result? We have removed the element 1, okay? So something is being removed on the left because our previous is less than to equal to our current median 2, right? 1 is less than 2. So need right now we're going to set to negative 1, okay? What does this mean? This means we need something on the left. We need an element on the left to balance out the one we've removed. Not really, like we haven't deleted it from our data structure, but we removed it conceptually. Like 1 is no longer in our heap. So we need to add like another element on the left to balance it out, right? But what are we adding? Well, we are actually adding 4, right? 4 is the element that is being added. 1 is the element that's being removed. And since 4 and 1 are being added into different sides of these two heaps, they're being added to two different heaps, we have a problem, right? Because now, since nums of j is greater than the median, our need is going to subtract by 1, and now it's going to be -2. Because, let's see, 1, 2, 3, 4. Okay, this is what we're doing, right? We're pushing to the right because, of course, we're going to push to our right. Our new element is greater than the median, so it should be pushed into the right heap, right? But because of the fact that 4 is greater than the median, now our median is no longer correct, because if we were to calculate the median here, okay, it would in fact be 2, right? Because we have 3 elements. I mean, this is like the real array, right? There were 3 elements, and we would just have this 2 here as the median. But no, we want it to actually be 3. So how do we fix that? Well, the idea is that if we keep track of this need variable, -2, that means we need to push things to the left, right? Negative means left. Negative represents left in this case. So we need to push something to the left. So we just simply balance it by saying if our need is less than 0, in other words, it's -2, we push from right to left. So we can balance these heaps, quote unquote balance, right? Because this heap is, technically not balanced, but it does give us the result that we want, which is the median is now 3, right? And we did that by pushing this over so that we get the result that we want. Basically, we're maintaining our 2 heaps, but with an offset, right? Our offset of 1, because this way we are able to maintain the correct median by letting the 2 heaps have different amounts of elements. Does that make sense? Let's say, for example, we changed our array to have this element instead be -1, okay? Instead of 4, we're adding -1. So we're taking something away from the left heap, but we're also adding something to the left heap. What does that look like? Okay? What does that look like? Well, what is the answer we're going for here? What is the median of -1, 2, and 3? The median is 2, right? So the answer we're looking for is 2. If we just go ahead, right? Let's see. Like, need is -1 right now, right? Because of the same thing. Our previous was less than or equal to the median. So need is -1. We're adding -1 to the left. So our heap is going to be like -1, 1, 2. And then on the right, we have 3. And guess what? Our median, the correct median, is still 2. As long as we don't move any elements from one heap to the other, our median is still 2. So that means that we don't need to do anything, right? Need, if nums of j, so the if this green element, right? If what we're adding is also in the left heap, that means that we have need is equal to 0. That means we don't have to balance anything. We don't have to change anything. Yes, I know that the left heap has 3 elements and the right heap has 1, but we technically still have the right answer because we removed an element from the left heap and then added another element. So for this window, right, our median is still correct if we just do nothing. That is what this need variable represents. I know it's kind of hard to understand, but that's what our code is doing. Based on the need variable, that is how we balance our heap, quote unquote balance it. I mean, technically it's unbalanced, but it's going to maintain the correct median, right? If we have our need being negative, that means to have the correct median, we need to push from the right to the left. If our need is positive, that means we need to push from the left to the right. If the need is 0, that means what we did balanced out the heaps already, so we don't need to do anything. Does that make sense? So that's the code we're about to write right now. Okay, doing this part again. So if to remove is less than or equal to the median, that means need minus is equal to 1. That means we are removing something from our left heap. That means that we need to put something into our left heap to compensate for that, right? If not, that means the element we're removing is going to go in the right heap. So we might need to add something to the right, okay? Now, whether we need to add or do nothing is determined by one other ingredient, and that is the element we're adding, right? Because here we're removing 1, but we're adding -3. So if 1 and -3 are like if we're removing 1 from the left heap, but we add -3 to the left heap as well, that means we don't need to do anything. Okay? So how do we express that? Well, if nums, remember the element we're adding is nums of j, right? For this index here, j, that's what this j represents. So if nums j is less than or equal to the median, that means we're adding something to the left heap. Okay, we're adding something to the max heap. So we no longer need something there, right? And if we're adding to the right heap, that means that we no longer need something there. Like, so these will cancel out. If we're removing something from the right heap and we're adding something to the right heap, now our needs balance out. But if we're removing something from the left heap and then we're adding something to the right heap, okay, then we're going to need to make some changes. And that's what we're going to write here. So if need is greater than 0, well, also before we do any of this, we're going to heap push to the left heap, which means we're going to have to push negative nums j to the left heap. And same thing here, we're going to push to the right heap. And this time we don't need to do negative anything. Okay, so all right, now the main thing is, depending on our need variable, this is where we balance the heaps if we need to by pushing one element from the left to the right. So if need is greater than 0, that means, and we can just copy paste this because this is the exact thing we're doing. We're just moving something from the left to the right. Else, and let's be clear here, if need is less than 0, we're going to push something from the right to the left. Okay, that's what this need variable represents. Okay, this part is really the hardest part of this whole code in general, right? This is the part that is hardest to understand, in my opinion. So take your time if you need to really understand how this works. Now, what we're going to do is, remember we have that whole idea of lazy deleting. So if we see something at the top of our heap that we can delete, there's no better time than now. 0 while right. Okay, so while there are elements in right, and remove dict. So when we find an element that we need to remove, we track it in our remove dict, and then we can check it to see if the element we need to remove is at the top of our heap. If it is, then that means that we can go ahead and track it in our remove dict and then go ahead and pop from right. Okay, it's the same thing for left. So while left and remove dict at the top of left is also greater than 0. Remember, since left it's a max heap, we need to set it to negative. So we're going to update our dictionary that's keeping track of all the elements we need to remove, and it's negative once again, and then we pop from the left. Okay, so this is the lazy delete being handled here. And now what is left to do? Well, we need to append our median to our result. So this code that, okay, this is a little bit ugly, but I can fix it. So this code will give us a median if the size of our heaps, if the count of elements in our heap is even, we're going to set the median to this. If not, median is going to be that. I think that's right. And then we append the median to our result, and then we can go ahead and return our result here. Okay, I'm just seeing if anything pops out at me as far as code that's wrong. Well, I'm getting the wrong answer here. So let's take a look. I made a little mistake here. This is obviously nums of I. I don't want to be pushing the the indexes. Okay, so we move this over here. All right, and one thing we need to make sure that we're doing is we need to make sure that our left, we're removing from our left heap, because it's possible that we don't have anything to remove in our right heap in the case of duplicates. So we actually want to prioritize removing from the left. And yeah, normally this will not matter what order these blocks of code are in, but in the case of duplicates, it can actually screw up your heaps if you're not removing from the left first. So keep that in mind, right? Check to remove from the left first, because we are prioritizing the left for insertions, right? So it's possible that if you're removing from the right first, you're going to get a heap with nothing in the right, and that will screw up. For example, in this case where you need to get an element from the right because you have even elements, let's say all your elements are the same. For example, all your elements are 0. If you put everything in the heap and then you remove from the right first, you're going to have just elements in the left. So it's not going to be able to calculate this median here. So prioritize adding to the left here, and also prioritize removing from the left. Okay, I know it doesn't make a lot of sense, and probably if you're not going to run tests, you won't need to really remember this, but for the code to work, it is something worth thinking about. So anyways, we submitted, and we are getting a runtime of 261 milliseconds. So we passed. And yeah, that's about it for this video. I hope it helped. And thanks for watching.